We've got two video lectures for this particular part of the unit. One is on motion and velocity and how you can make a displacement versus time graph. And the second video lecture is going to be on motion maps. The reason I split this up into two separate things is that one goes into the other one, but they're kind of different as far as the setup. So that way, if you're having trouble with one and not the other, that way it's a little bit easier for you to go through and pick and choose, so you don't have to go onto YouTube and go all the way through a longer lecture or something like that. So that's why they're into two separate parts. Hopefully that's okay. If not, I don't know. It's already done, so there's nothing we can do about it now. So we have looked at our modeling unit. You did a lab where you had buggies that were moving a certain distance and displacement over a period of time. You recorded that data, and we made a graph, and we talked about it. Now, through our discussion, we actually looked at that things are moving in space at a given time, and that we had a couple of different carts that we had. Nobody knew at the time. You did, because you folks are smart. And some of them went a further distance in the same amount of time. So that was the question that we had to ask ourselves in class is, well, what do those two things mean? And through our discussion, we found out that, well, this one on our green line, and they were the red buggies for our particular class, were actually moving faster. So in the same amount of time, they were moving a further distance. And when we looked at density, we were able to actually come up with a mathematical model using nothing but our graphs. And remember, we're big on that right now. We don't want to have to do more algebra than we need to. So what we were able to come up with in class was, well, because we have our y-axis and our x-axis, there's got to be some relationship between distance and time. It's not always going to be the same thing. And again, our conversation led us to velocity. So now we can actually use our graphs to come up with distance, time, and velocity using 2 points or so, or 1 point and being given a velocity, because this is just a slope of our line. That's all it is. And again, rather than having to say, well, what's the time if something has a certain velocity and travels a certain distance, now you're doing algebra, right? Where, okay, now we get time on its own, so we've got to take time and multiply that by velocity to get distance, but we're actually looking for time, so then we've got to divide that out, so that time is actually distance over velocity. That's a lot of algebra, and we could do it, but isn't it a lot easier to just go, okay, dot, 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 down, 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 there's our time. That seemed a lot easier, a lot less things that we need to keep straight. Doing it this way, there's a lot more things that can go wrong. As long as you know how to set up your graph and how to properly read it, you're good on almost anything. So let's go through the slides a little bit. So again, displacement versus time graph are used to show an object's position at a certain time. And this is kind of our setup. Again, remember, please, that these slides are online. So that way, if things are going a little bit too fast for you, you could pause this. Or if you can't see things because you get to see me up in the corner being all crazy and you need a little bit less distraction there, then you can write those down as well. Sometimes we call displacement position. I understand. So if you're stumbling onto this YouTube thing, that there is technically two definitions for displacement and position, but where we're at in this course right now, we're going to kind of treat them as the same. So if you see position, treat that as displacement. Remember, displacement can have a positive and negative because it's based off of where you are at compared to some reference point, either your starting position or some object that you want, like your house. So how far away you are from your house. You will always put your position or your displacement on your y-axis. Now, a lot of the ones in this slide will only have a positive y-axis, but you can have a negative y-axis as well. And we'll see that in some of the homeworks, but it just makes these slides a little bit easier so they don't get too cluttered. And then time is always going to be on your x-axis. And then, like we talked about in class, your slope is x over y. So that means velocity is your position or displacement over time. You guys can do this. Remember, we've had a lot of practice in a regular math class where you just have regular variables that really didn't mean much to you. And now we're actually plugging in real world values and real world consequences into just generic X and generic Y. So that's where these graphs come in, where instead of just saying Y, how much Y, what's the slope, and it just means nothing, we're actually getting a velocity from something that was moving in real life. And that, I think, is kind of cool, that you can take something that's just numbers and letters and a jumble that you're learning the sequence of things, but now you can actually apply it to something real in your real life. So let's look at an example problem. Let's say you have a runner and you've been given some data. You want to track his time for a track meet training, and you get this data. And you mark off every 50 meters, and you click and see how much time it takes that person to run 50 meters. So you might want to pause this right now and actually go through and make this graph. You need to have this in your notes. So if you want the data, that's fine, but you at least need to have the graph. You need to then figure out what is his speed or his velocity going to be. You can literally choose any point on the graph that you made and go and find your slope by doing rise. So rise is going up and down, divided by run, or y divided by x. And in this case, you can literally choose any points that are on your graph. Now, just as a helpful suggestion, if you have been given guide marks for any of your graphs, meaning that there's lines kind of telling you where these numbers are, pick a point that goes through one of those because you know for sure. So if I had a guide mark that told me this was 5, and this was 10, use those because you know for sure what that means. Yes, you can go, okay, the next one up, but it might be between something, so now you're trying to divide by decimal points and all that kind of good stuff. And while it's doable and you might want to spend more time on your science homework, I know I wouldn't. I would want to be as efficient as possible and get the correct answer and put the knowledge in my head and then move on. So your graph should come out looking like the one that's on the screen here. I think I'm in the top left, so down here somewhere if you're looking. There you go. So you can then find his speed as he moves. Every 10 seconds, he moves 50 meters. So what we do there is just take 50 meters. Remember, units, important, otherwise they're pies or whatever. In 10 seconds, so what we get is 5 meters per second. Look at that. We didn't have to do all the algebra. Now, this one is just division. But where it makes this easier, we'll talk about in a few slides. Again, try to make another position versus time graph. So this car, it tells you every 1 second intervals where it's at. So again, pause it, try to make a graph. Because again, if you're having trouble with this, this is where you need to come to class with some questions, folks. So that way we can answer these, move on, and you have as much time to work on the homework as possible in class. And we're moving forward with things that you have built rather than something that you read in the book or something that I just told you once and then just like, here's your homework, do it at home at 11 o'clock at night after football or field hockey practice or whatever it is. So again, the points are there. So 1 second, he's at 10 meters. 2 seconds, he's at 20 meters, so on and so forth. You should have gotten a graph that looks like this. You now can get lots of information from this. First off, what's the car's velocity? Pick points that are already measured for you. Make your life easier. Come back a second. Okay, I'm back. So again, from this, you can now divide it out because you took your rise or your up and down, divided by your left and right, and there you go. So we know that the velocity is slope. Cool. So again, we know that this is the ratio of your x-axis and your y-axis. And just at looking at your graph, and this is, again, we're looking at things graphically is really cool, without needing to do all the math. Again, we're trying to cut out as much math as possible. Shh, don't let anybody know. If velocity equals slope, how can you tell which has a greater slope? It goes up in the least amount of time, so it kind of looks steeper. You can now look at a graph, and if somebody says, look, between the blue and the green, which had the higher velocity? You could, and fairly enough, if your numbers on here, go through and do the math. Do the math. You know what? I don't want to have to do that. This one has a greater slope, so therefore we know the velocity has to be. Because again, slope is velocity. So if this one is steeper, it has to have a greater velocity. Just there it is. Now if I ask you for a number, say, well, what was the velocity? Okay, now you actually have to do some math. They've kind of, put you in a corner. Sorry. But until I ask that question, if you just have two objects on the same graph, meaning that they were graphed over the same period of time, and somebody asks which has the greater slope, all you have to look at and see which one is steeper. And it also works in the negative direction too, but we'll get there in a second. So again, the steeper line is the faster speed. This is supposed to be working. It'll work on your a GIF versus Jeff. It's supposed to be working. So your blue car is moving slower than your red car, and therefore the red car has a steeper line. Again, it's not working out too well when I'm doing this, but there you go. So when it comes out, the red car has a steeper line than the blue car, so you know, hey, red car had to have been traveling faster. Could you calculate it out using the numbers that are right there on the slide? You could. And if I ask you what the velocity of the red car was, okay, well, then you have to do it. But until that question comes up, you don't have to do any math. Think about that. There you go. So what are negative slopes? These ones look normal, but what happens if we start going and have a slope this way? Well, remember what this is. We are graphing displacement, not distance. Because can you have a negative distance? No, you keep adding that up, adding that up. I keep moving, I keep adding. You can't owe somebody a distance. You either ran it or you didn't. You walked it or you didn't. That's future you. So remember, this is your position based off of an origin. So maybe your house. Okay, so let's tell a story here. Because you worked with displacement a little bit and that. So let's say you leave your house and you go to a restaurant. There you go. And then you stay at the restaurant for a while. Remember, displacement. Horizontal lines mean that's not moving. So that tells us what about our velocity? Our velocity is 0. We have no change in distance, so therefore we have no speed or no velocity. See how we're now looking at the slopes and getting lots of information without doing math? That's the beauty of it. Now let's say you don't feel too well. You took the Quaker Steak Atomic Wing Challenge. Like, woo! Oh, man. And you know what? You don't want to be at the restaurant anymore. So now you want to get back home, and you are still following the laws, but you take every shortcut that you can to get back home. Which has the steeper slope? This one does. Again, you're headed towards your destination, so that's all negative velocity means, is that you are having a speed, but going back towards whatever your reference point is. That's all it is. That doesn't mean you're going backwards unless you have a reference point that you're moving away from or towards. Does that make sense? Because technically you can drive a car backwards to the restaurant. I wouldn't do it. It's illegal and very dangerous. But you would technically have a positive velocity because you're moving away from your reference point. And then you turn the car around, you're sick. You're like, well, let's not do that little game where I tried to back up to the restaurant. I'm sick. I need to get home. So you're like, oh, okay. Again, it has nothing to do with the forward or direction of the object moving. It has to do with where you are from whatever reference point you're using. In this case, your house. So again, you have a less steep slope on the slide here. That means that it's slowing down. So as the slope gets less and less steep, that means you're slowing down. And then you start going backwards. So here, boom, you have no velocity because you have zero slope. Because you're at the restaurant, you're not changing your position. And now you have a quick going backwards. So again, you could say speeding up or slowing down. But again, this is based off of your reference point. So this is a very, 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 very good thing to have in your notes. The curved line we're not going to talk about so much right now. We'll get there. But the green line and the red line, you should be able to look at that, and that will help you with the homework this week. It will also help you with your lab practical that's coming up after we work with this for a little bit. So again, pause it and write this down or jump over to the slides and make sure this gets in your notes for sure. We're going to skip that one, okay? So here's another example. Try it on your own. We're not going to lecture about it. But your graph should end up looking like this. This is what we're working towards, folks. You should be able to take a story problem and make a graph from it. Or you should be able to look at a graph and write it down. Oh, this person or thing was moving away from their origin. They stopped for a little bit, and then they went backwards towards their house or whatever it is. Good? So again, this is explaining what I just mentioned. So hopefully if you didn't get this when you went through and did it and you paused it, then you have questions to come to class with. So again, how can we do this to then predict things without using algebra? That's what I've been promising now for a couple days. Well, here it is. Let's say that you have another runner that you're helping to train. And this time, you know what? You weren't given a lot of data points. When you had the gentleman before, you had all these data points and things were really good. But let's say that this girl's like, hey, you helped that guy out. Could you help me? And you're like, I've already picked up half my stuff. I'll help out where I can. And you only have 2 data points. Well, draw a position time graph for this or a displacement time graph for this, just using your 2 points. And then what you're going to do is just keep drawing your slope out to as far as you want it to. Because as long as your velocity is constant, you will know these points will always be the same, and you just can read your graph to get different points. So let's look at that. So there you go. That's the line that you should have gotten. And now let's do this without math. We could now get a bunch of stuff. So you can predict how far things are going to go. So how far is it going to go in 4 seconds? You can tell there used to be a... Okay, I'm back. It cut me off. So now instead of needing to throw things in algebraically, right? We only had 2 points before, and you extended this out as far as you could. And now instead of saying, well, you know that the runner has a velocity of 10 meters per second. How far do they go in 6.5 seconds? Well, now you've got to rearrange this to go over here. So now it's 60.5 meters. Now, let's say your algebra isn't that strong. Or you could just go to 6.5, over. And guess what? That's going to be 60.5 on your graph. How much math do you have to do? 0. The only thing is, if I would ask you what's the actual velocity, you have to do division. Up and down, over the left and right. There you go. And then the negative will tell you if it's coming towards or away from the origin. If you have two things, the thing with the greater slope has more velocity. There you go. Now, this only works, and I know, but for right now, we can leave it be like this. This only works if velocity is held constant. As of right now, so that's why you have to make sure that your lines are pretty straight so you can get the best numbers that you can. Okay, we'll work on things that maybe things will change in the future. I don't know. Actually, I do know. But for right now, we are going to keep things pretty good. Now, you've sat through a good 20-minute lecture, and you've got another one to go still. I want to reward the folks that are sitting through this. So you need to know 3 things. Put them in your notes, because we will be doing something in class where you are allowed to use your notes. Ooh, so what do you think is going to happen? If you sat through this entire lecture, I have a jersey on. First week of football season for this year. Yay. And as you know, the Fern's a big Jags fan. I root for the Browns too, but you know, I'm not buying a ton of jerseys. So the 3 things you want to write down in your notes is the number of the jersey that I've got. It's number 32. There you go. You want to write down the gentleman's name, Maurice Jones-Drew. Great running back, underrated just because he was on some bad football teams. And one that I'm not going to write down because we might have some people fast forward through this and try to find this is why he has number 32. And again, write this in your notes. He was number 32 because he was picked number 32 in the draft, and he knew he was good, and he knew 32 other teams passed up on what he could do for them. That's also a lesson for you folks. If you know you're good at something, keep trying even though a bunch of people pass you up, because eventually you'll be given your shot and make some good things happen. Again, if you did these examples and they weren't making sense when you came out of pause and found the answers, then please come to class with discussions. That's what this whole modeling thing is about, is that you made this up. You guys put this together yourselves as a class, that velocity is actually the slope. We're just filling in some of the background information as far as, okay, greater slopes for more velocity, that kind of thing, because we only have so much time in class to do this. Now, if you have 0 questions, you will be getting 5 worksheets that go along with this, and if you still don't understand, you're not going to be as good at the worksheets, and it's going to give you more homework because we're going to look at these worksheets over 2 days in class, but you still have to get them all done. So if you know this, and you're like, boom, I've got a question, that's the one thing I didn't, oh, awesome, and you're just able to go through these worksheets. They're designed to be done in the class time that we're giving you. But if you have questions, it might take you a little bit of time at home. We want you to spend that time because we want you to get to where you need to be for your quiz and your lab practical. I'll catch you later. Please watch the motion map ones because now you're actually going to learn how to put this into more of a 2-dimensional thing, graph rather than your traditional line graph. And you will be, and eventually what you need to be able to do is go from your traditional line graph to a motion map to words and back. So words, motion map. And if you could do that by the end of this chapter, and find where and be able to interpret that, you will have no problem with your lab practical, because it's going to basically be either taking something that we have done in real life and making a graph about it, or making a graph and telling us what's happening in real life. Easy enough if you know how to do all this stuff. And there's actually 3 ways you can do it. You can either do it algebraically if you're strong at that,